Hello, and welcome to part 1 of a new series, Programming 3D Graphics, from scratch. In this series, we're going to start from nothing and develop quite a feature-rich software rasterizer, which will allow us to explore 3D graphics in an interesting way. The example I'm showing on the screen shows the one-lone coder phrase rendered using a full 3D rastering pipeline, and you can see it's even shaded and lit accordingly. I've implemented a first-person shooter style camera, and we can elevate the camera up and down too. Now we won't get quite that far in this episode, as this is just episode 1. We're really going to look at the fundamentals that are required as part of a 3D engine. But as the series progresses, I'm going to add more and more features to turn it into quite a sophisticated 3D engine. Now, when you hear 3D engine, you might think of the terms OpenGL, DirectX or Vulkan these days. We won't be looking at those exactly. Instead, what I'd like to present is the theory and the mathematics and the ideas that go behind the graphic APIs that we know and love. And what I hope to show by the end of the series is just how complicated it is to make your favourite games look very pretty indeed. And I'll demonstrate that the number of calculations per triangle and per pixel is simply huge. Now there's one thing we can't get away from with 3D graphics, and that is mathematics. But don't click stop just yet. I'm going to try and present it in a style that's maths friendly. And the nice thing about 3D engines is even if you don't have strong mathematics ability, you can still use most of the parts of a 3D engine as black boxes. You don't necessarily need to know how they work, but you need to know what these magical functions do. And over time, by using such functions, you can actually develop a really intuitive understanding of what's going on behind the scenes. So let's get started. Rather oddly, I'm going to start this tutorial by saying there's no such thing as 3D graphics. And that's simply because if we try to represent a 3D shape on a screen, of course the screen is two-dimensional. So even though the object looks 3D, what we're actually trying to generate in the end is a sequence of 2D shapes that give the illusion of 3D on the screen. So taking this cube as an example, I can say I've got a top piece, and I've got a side piece, and I've got a front face. Should be a little squarer than that. And so the purpose of a 3D engine is to take three-dimensional geometrical data and convert it into these 2D shapes. So we might define our cube as being a series of 8 vertices, which I'll mark here with the red dots. And don't forget, there's one we can't see. And from this very early stage, even though it might seem strange, I'm going to suggest that all of our dots are grouped into triangles. So this front face here, I'm marking out in blue, consists of 2 triangles. And the same applies for the top face and the side face, and even the faces we can't see in the background. And the reason I'm doing this is a triangle is a very simple primitive. In fact, it's the simplest 2D shape. And as will become apparent, it's convenient to group vertices together in some meaningful way. And because triangles are the simplest 2D primitive, it's possible to represent any two-dimensional shape using nothing but triangles. And finally, when it comes to drawing triangles on a screen, there are some very optimized algorithms to do this, because a triangle consists of straight lines. Well, not straight when Javid draws them. And there are also some neat algorithms to fill in a triangle and shade it on the screen, again using straight horizontal lines. We'll look at rasterization in a later part of this series. But what I'm trying to emphasise is that triangles, they're really important. And so in this video we're going to look at how we can take a collection of vertices in three-dimensional space, form a surface of a solid object out of triangles, and project these triangles to the screen for the user to see. Now, because this is a new series and I'd like to show how to do this from scratch, I'm actually going to show you how to create the Visual Studio project necessary to do this. And in part, that's because Visual Studio 2017 has changed the way projects are created. And so I feel it might be useful to demonstrate how to set up a project to start something from scratch. So I'm going to go to File, New Project, and I want to choose Windows Console Application. Of course, I'm going to be doing all of this with the console game engine. But don't let that put you off, simply because the maths and the ideas don't change, regardless of the interface that you're going to use. Select a console application and give it a name. I'm going to call this one OLC Engine 3D. Now, in previous versions of Visual Studio, when you click OK, it would give you some more options. It no longer does this. Instead, it creates a project for you and fills it full of files. Well, the first thing I'm going to do is delete everything except the .cpp file that it has created for me. Bye bye. I'm then going to remove this line, standard AFX, that's for the pre-compiled headers. I'm not interested in using those, and even though I've removed the line, I actually need to go into Properties of the project, go to C++, expand that open, and choose the pre-compiled headers option, and tell it that no, I don't want to use pre-compiled headers. And click Apply. What I do want to use is the console game engine, so I'm going to include it. And I'm going to make sure that the header file that contains the console game engine is also in the project directory. There we go. And I'll add that file, just because I like to see all the files my project is using, into my Visual Studio project. And of course, if you're on a different operating system now, you can use the OpenGL version or the SDL version of the console game engine. Even though it says game engine in the title, all we're really doing here is accepting input from the user and displaying things on a 2D screen. The fact that it has game engine there doesn't imply we're going to be using any of the game engine features. Which is important, because I don't want you to think that I'm hiding interesting technology and clever functions in the console game engine and exploiting them to generate 3D graphics. I'm not. Regular viewers of the channel will know that we need to create a subclass of the OLC console game engine, and so I'm going to call it OLC Engine 3D, which inherits from the console game engine. Let's just give it a quick constructor. And there are two functions we must override. The first is onUserCreate. And the second is onUserUpdate. For now, I'll make these return true, and that tells the game engine that everything is fine and it should continue running. In our int main function, we need to create an instance of this class. And we should try to create an instance of the console using it, using the construct console function. And for this application, and indeed this series, I'm going to use quite a high resolution console of 256 characters wide by 240 characters high, and each character is going to be 4 by 4 pixels width and height. And oh dear, quick error number 1, I need to publicly include the console game engine. There we go. So if we can successfully construct the console, I want to start it. Else, I would display some sort of error message. As is typical in some of my videos, I don't tend to do all of the error capture code. That's to keep the code as clear and concise as possible. Finally, I'll name the application 3D Demo. And a quick reminder, by default now, Unicode will be enabled. And this is important because I think it is the singular most popular question I've been asked since starting this channel. How to enable Unicode. And thankfully Microsoft do that for me now. Well done. Now because I want to demonstrate all of this from scratch, I'm not going to be using a maths library to help me. We're going to do absolutely everything. So I'm going to create a structure called vec3d. And this is going to hold 3 floating point values, x, y and z, which represent a coordinate in 3D space. I'm also going to create a second structure called triangle, which is going to group together 3 vec3ds. As the series progresses, we'll be adding more features to this triangle structure. Finally, I'm going to create a third structure called mesh. And a mesh is going to represent the object. It's going to group together triangles. And you'll notice a little red wiggly line has appeared. And that's because, at long last, I've finally removed the using namespace std from the header file, as I can hear most of the people on Discord cheering right now. And I can't argue that it is good practice not to include using namespace in your header files, but to keep this code clear, I'm actually going to use it here. So a quick recap, we've got a mesh which contains a vector of triangles that represents an object, and we've got a triangle which contains 3 vertices, or vector 3ds. These are the points that define the outline of the triangle. I'm going to add now to our main class a mesh, and I'm going to call it mesh cube. And in onUserCreate, I'm going to populate that mesh with the vertex data to define a cube made of triangles. And I'm going to use this with some nifty initializer lists. I'm going to keep the cube simple and define it as a unit cube in these 3 dimensions. So each side of the cube is 1 unit long. And we'll assume the origin of the cube is at 0, 0, 0, x, y and z. Therefore this point becomes 1, 0, 0, 0, 1, 0 and 1, 1, 0. I've drawn the cube edges so we can see what's going on a little more clearly, and this obviously becomes 0, 1, 1. In fact, each one of these coordinates at the back is the same as the one at the front, except the z component is 1. So this one up here is 1, 1, 1, and this one is 1, 0, 1, and the one hidden is 0, 0, 1. And I'm going to adopt the convention that this face is south, the face round the back is north, this face is east, and that face round the back there is west. This one's the top, and therefore the one underneath I'm going to call bottom. And now I can start to think about my triangles. But there's something important about the triangles which we'll come to again later on, and that is the order of the points that we define the triangle in. And I want to always use a clockwise order. So I'm going to take from 0, 0, 0 up here, all the way along, and because it's a triangle, I now need to come back down to the original point. But you'll notice I've gone in a clockwise direction. And I want to do the same now for my second triangle. Up to the top, back down, and along. Again, in a clockwise direction. And I want to do exactly the same for the remaining faces. Always retaining this clockwise ordering. Using initializer lists, I can define the vertices manually, and I've grouped them into south, east, north, west and top and bottom. But I'm also using a neat trick that I've got an initializer list inside the other initializer list. So this sub-initializer list will initialize the triangle with 3 vectors, whilst the outside initializer list initializes the standard vector. I'm going to use the fill command in onUserUpdate to clear the screen, from the top left to the bottom right. And after we've cleared the screen, we're going to need to draw our triangles. And because our triangles are neatly contained inside a vector, inside a mesh, I can use an auto for loop to iterate through them all. But of course, it's not this simple. The objects exist in 3D space, and the screen is in 2D space. So we need to come up with a way of condensing that 3D space to the 2D screen, and this is called projection. So how do we turn our 3D vertices into 2D vertices for projection onto the screen? Well, first of all, let's define our screen, which is going to be some sort of rectangle with a width and a height. Because screens come in all shapes and sizes, it's useful to reduce the three-dimensional objects into a normalized screen space. And so I'm going to suggest that if we partition the screen this way and this way, and we label this as -1 and this as +1, and up here as -1 and this as +1, we've normalized the screen space. Obviously that gives us 0, 0 in the middle of the screen. And because the width and height can be different, we want to scale movements within the screen space accordingly. So we're going to use the aspect ratio, which I'll call A, and define that as being the height over the width. And this will be the first of several assumptions about how we're going to transform our 3D vector, x, y, and z, into our screen space vector. And I'm going to demonstrate this by accumulating the operations required. Normalizing the screen space has an additional advantage, that anything above +1 or below -1 definitely won't be drawn to the screen. So let's just draw in some imaginary boundaries here. This object exists entirely within the visible viewing space. But this object on the right straddles the boundary, so we'll never see this side of the object. However, humans don't see screens in that manner. They see instead what's called the field of view. And we can cast a ray that way, and we'll cast a ray that way. So at this point it's -1 and +1 on the screen, but also out here in our space, this is also -1 and +1. And of course this makes a lot of sense, because objects that are further away, well, we can see more space the further away it is, and as we approach the screen, we occupy more of the screen with our objects. If the field of view is particularly narrow, which I'll crudely draw in here as a blue triangle, it has the effect of zooming in on the object. And if the field of view goes really wide, it has the effect of zooming out. We see more stuff. And this means we need a scaling factor that relates to the field of view, and we'll say that the field of view is theta. Well, one way to think about a scaling factor is to draw a right-angled triangle right down the middle of our field of view. Say that they're right angles. And as this angle increases, so this is now theta divided by 2, our opposite side of the triangle increases. And so it stands to reason that since we've got the angle of a triangle, its opposite side and its adjacent side, that we might want to consider looking at the tangent function. But of course it's tangent of the field of view divided by 2. But there's a slight problem here. If we take a point and we increase our field of view, the scaling factor that we get as a result of this equation gets larger. And naturally, if we reduce theta, the scaling factor gets smaller. So this has the rather odd effect that if we increase the field of view, we start displacing all of our objects outside of it. And naturally, if we decrease our field of view, we scale them less, so more objects can appear. And this is a contradiction to what we've just said, that increasing the field of view is the same as zooming out. So what we want is the exact opposite of this. Indeed, we want the inverse of it. This gives us some more coefficients to add to our transformation, where f is equal to 1 over tan of theta over 2. Since we've gone to the trouble of normalising x and y, and realistically all we're interested is in x and y because this is a 2D surface in the end, we may as well also attempt to normalise z. And the reasons for this might not be immediately apparent, but as we'll see in future videos, knowing what z is in the same space as x and y can be really useful for optimising our algorithms and handling other interesting drawing routines like transparency and depth. Choosing a scaling coefficient for the z-axis is somewhat more simple. Drawn again a frustum, and this is the z-axis going forward into the distance. The furthest distance of objects that we can see will be defined by this plane at the back, which I'm going to call z far. Now you might assume that means where the screen is at the front, that would be 0. But that's not quite the case, because the player's head isn't resting against the screen. The player would injure their eyes. In fact, there is a small distance here. And I'm going to call that z near, which is the distance represented from the player's head to the front of the screen. And z far is from the player's head to the furthest distance we want to be able to view in the engine. If I put some imaginary numbers next to this, so let's say our far plane is at 10 and our near plane is at 1, to work out where the position of a point in that plane really is, we need to first scale it to a normalised system. So in this case, our z far minus our z near is equal to 9. So we want to take our point and divide it by 9. That will give us a point between 0 and 1. But we've decided that our far plane should be 10, so we need to scale it back up again. So this is implying that we have, for our z-axis scale factor, something that looks like this: z far divided by z far minus z near. But this still leaves us with a bit of a discrepancy here. So we'll also need to offset our transformed point by this discrepancy scaled too. Well, fortunately, we know where that discrepancy is. So we can take our equation up here and simply multiply it by z near. But we're going to offset it from the final result. So this becomes z far multiplied by z near over z far take z near. And so now if we look at our initial coordinate and look at the final transformed coordinate, well, it's starting to look a bit complicated. And we're not even quite finished yet. Intuitively, we know that when things are further away, they appear to move less. So this implies that a change in the x-coordinate is somehow related to the z depth. In this case, it's inversely proportional. As z gets larger, i.e. further away from the screen, it makes the changes in x smaller. And this is analogous for y. So our final scaling that we need to do to our x and y coordinates is to divide them by z. Let's start to simplify some of this out. We'll take our width and a height and we'll call it A for aspect ratio. We'll take our field of view and we'll call that F. And let's take our Z normalization and we'll call that Q. And which you can see also applies here. Which means a much simpler form would be AFX over Z, FY over Z, and ZQ minus Z near Q. We could go and implement these equations directly, but instead I'm going to represent them in matrix form. as this allows us then to implement a function which can multiply a vector by a matrix, something which we're going to use a lot of in 3D graphics. In the Code It Yourself Asteroids video, I already talked in quite some detail about how matrix multiplication works. But just as a quick recap, we'll take this element of the vector and multiply it by this element of the matrix, and this element of the vector and this element of the matrix, this element of the vector and this element of the matrix, and we sum them up, and that gives us a result to put into our new vector in this location. So let's start with the transformed x location. So I'm going to put the result here. Well, in the top corner we simply want AF. The remaining entries are 0. So x multiplied by AF plus y multiplied by 0 plus z multiplied by 0 gives us AFX. Y is even simpler. We're not too concerned about the x component, we just want f and nothing else. And similarly for the z, we don't care about the x component either, nor the y, but we do concern ourselves with q. But we've got an interesting addition to z, that we've got to have this little offset. That's okay, because as we're performing the matrix calculation, we're summing this column multiplied by the vector. So I can simply include as one of the elements minus z near q. But hang on, we've suddenly got 4 elements in this column, and we've only got 3 elements of our vector as an input. So to make this happen, I'm going to extend our input vector with a 1. This of course also means I have to put in additional zeros for the x and y elements. But now I've got an interesting scenario of multiplying a 4x1 vector by a 3x4 matrix. I have to use the final column of a 4x4 matrix to make this legitimate. So let me just fill in zq minus z near q. So what do we do with this 4th column? Well, you may also notice that we've not got a divide by z anywhere in there. And I can't readily do that in this calculation. Getting the divide by z is going to need to be a second operation. In fact, we're going to be normalizing the vector with the z value. So I do want to extract it. And to do this, I'm going to 0, 0, 1, 0. So this will give me a 4th component of my transformed vector, which will simply be z. And after I've performed the transformation, I'm then going to take the last element of this vector and use it to divide the others, giving us a coordinate in Cartesian space. And so when we bring this structure all together as one, this is called the projection matrix. And yes, it may seem like a scary bunch of maths, but this is actually probably one of the more complicated transforms that we'll need to do as part of the 3D engine. And as I've mentioned before, you can really treat it like a black box. This projection matrix will work for all 3D applications, and it's highly customizable in terms of aspect ratio, field of view, and viewing distance. So this means, of course, we now need a matrix structure. I'm going to call it 4x4. And I'm simply going to define a 2-dimensional array explicitly and initialize it to 0. And the ordering of this matrix is row followed by column. I'm going to populate the projection matrix once in onUserCreate, because the screen dimensions and field of view are not going to change in my application. We'll have our near plane distance along the z-axis. I'm going to set that to 0.1. We're going to need the far plane, which I'm going to set to 1000. Let's not forget the important field of view, which I'm going to set to be 90 degrees. Next up is the aspect ratio, which I'm going to grab directly from the console, so it doesn't really matter what size console you create. And for convenience, I'm going to do the tangent calculation as a one-off. And you'll notice here I've converted it from degrees to radians. Let's create a projection matrix. matproj. That's quite customary. And I'm going to specify the elements of the matrix directly. Row, column. So we know that this is our WX value that we've just seen in the slides, which was our aspect ratio times our tangent calculation. Our HY value was just the tangent calculation directly. And here I've just filled in the remaining options. I've got a sneaking suspicion that we're going to be doing matrix vector multiplications a lot. So I'm going to create a function to do it for me. And so we're going to input one of our vectors, and I want to get a different output vector, because I don't want to upset the input data. And we need to pass in the matrix. Performing the multiplication is simple, and I'm going to write the x, y and z components directly to the output vector. But don't forget, we had a mysterious fourth element, which I'm going to call w, and we have to include this when we're multiplying by a 4x4 matrix. The only thing to remember is that we're implying that the fourth element of the input vector is 1, so we can simply sum the final matrix element. Now, because we've got 4D and we need to get back to 3D Cartesian space, we're going to divide it by element W. But I don't want to do that if W is equal to 0. That's going to cause me headaches. So if W is not 0, then I want to take the output values and divide them by the W. Now let's have a think about how we draw the triangles using our projection matrix. We know that we're going through this auto for loop, picking out each triangle at a time. We don't want to upset the original triangles, so I'm going to create a new triangle called try-projected. And try-projected is where I'm going to put the result of my matrix multiplication. So we've got the input try-projected as the output, and matproj as the matrix we're going to use in our multiplication. However, we can't use the triangle directly, and we need to reference the vertex inside. And I'm going to repeat this for the 3 vertices. I could stick that in a for loop, but I like the fact that it's explicit. Quite a while ago now, I added to the console game engine the ability to draw a triangle, and this simply draws 3 lines between the 3 coordinates that are specified, using the original drawLine function, which has been around since the beginning. This makes drawing the triangle a little simpler. I'm going to take the x coordinate, and we'll do some cut and paste here just to speed it up a little bit, and the y coordinate of 0.1. And we'll do 0.2 and 0.3. And the final 2 arguments are how it appears on the screen, so I want to use solid pixels. And I'm just going to draw everything in white. So let's take a look. Well, I can't see a cube there, but what I can see, right up in the top corner, is a single pixel. And in a way this is to be expected, because our projection matrix has given us results between -1 and +1. So now we need to scale that field into the viewing area of the console screen. So the first thing I'm going to do is take a coordinate and shift it to between 0 and 2. I'll do that for both x and y. And I know this is where people will be screaming at me, why are you not making a special vector class? Why are you not using operator overloading? And we'll come to that in later videos. So let's do that for all 3 points. So now it's between 0 and 2. I want to divide it by 2 and scale it to the appropriate size for that axis. So I'll take the x and I'm going to multiply it by half times the screen width. And you'll see here I've just done it for the other 2 vertices as well. So let's take a look. Well, I can certainly see what looks to be a cube and some triangles, but Something's not quite right. There's no perspective on this, and I'm not really sure of the orientation. So what can be going wrong here? Well, simply put, our cube has its origin at 0, and our current view into the world is also at location 0. And so this means our face, for example, could very well be inside the cube at this location. That means some of the cube is behind us and we're still trying to draw it, and this is undefined. So it's not unsurprising that the result is a little bit useless at the moment. What we need to do is translate our cube into the world, away from where the camera would be. So instead of projecting the triangle directly, I want to translate it first. And this is easily done for translation, and all we want to do is offset the triangle in the z-axis into the screen. So we'll add 3 to all of the z components of the triangle, into our new triangle, Triangle Translated. So this is no longer the triangle we wish to project. Let's take a look and see if this has made it any clearer. Perfect. We've definitely got some perspective action going on now. But because the scene is static, we can't really get a feel for what's happening in 3D. So I'm now going to rotate the cube around its x and its z-axis. I'm not going to do the rotations at the same speed because we'll become a victim of what's called gimbal lock. So I'll bias the rotations per axis differently. I'm going to add 2 more matrices that can perform the rotation transform around a specific axis. Now, I'm pretty sure the mathematicians out there will start screaming, well, surely we can combine all of these matrices with matrix multiplications. And we can, but I'm not going to do in this video. To give the impression that something is rotating, I'm going to need an angle value that changes over time. So I'm going to accumulate the elapsed time in a variable called f theta. And I'm going to hard code 2 rotation matrices, one for the z-axis and one for the x-axis. You can look these up on Wikipedia, it's fairly standard. And they work in quite a similar way as the rotation matrix that I derived in the asteroids video. Since we're not multiplying matrices just yet, I'm going to need more triangle states for the intermediate transformations. And I still want my translation to be the last thing that I do, because the order of transformations is quite important. I want to rotate it around the origin of the object, which is currently 0, 0, 0. And then, once it's rotated, I want to translate the rotated object further into the z-plane. So, taking the original triangle, the first thing I'm going to do is rotate it in the z-axis. The second thing I want to do is rotate it in the x-axis. I then want to update my translation code to use the most up-to-date triangle. So now let's take a look. And immediately I think that's perfect. Look at that, a perfect cube projected evenly and nicely onto the screen, rotating smoothly, and the triangles and the faces are very visible. And so that's that for part 1 of this series. In the next part we'll be looking at how we can control the camera, and we'll also be looking at how we can shade the faces of the object. As usual, all the source code is going to be available on GitHub. Please join the Discord server and come and have a discussion. If you've enjoyed this video, give me a big thumbs up please, and have a think about subscribing. Until next time, take care.